Welcome to the second video tutorial on TKGate provided to computer architecture students enrolled in the Laurea degree program in applied computer science at the University of Urbino. This is the second video tutorial so that if you want to find general information about TKGate and about its basic features, please refer to the first one. Today we are using TKGate to design a 4-bit ripple carry adder. So we launch TKGate and we open a new project called my RCA4, where RCA stands for ripple carry adder and 4 represents the bit width of our target component. Okay, in order to design a ripple carry adder, we need first of all to know something about its reference architecture. And its reference architecture is represented in this slide. So we will make use of smaller components which takes into account 1 bit at a time, or actually 2 bits of the same weight taken from the 2 operands at the time, in order to compute 1 bit of the sum and possibly propagate a carry. This component, as you know, is called a full adder. So at the top level, we need to create modules suitable to implement a full adder and to decide how to connect them together. So let's start by doing this. So as you know, we can make a module instance and well, before doing so we needed to click on a point in which we want a module instance to appear. So let me do it again, module instance, and I call it my FA, which stands for full adder. Okay. Then I resize it and I add input and output ports. I call this port A, this is second input port B, then there will be another input port called C in, which stands for carry in, then an output port called S, which is the sum bit, and then another output port called C out. Please don't forget to set the interface of this module. So having the module selected, we need to go under the module menu and click on Set Interface. Okay, Set Interface makes all the input and output ports part of the interface of this module, so that when we go inside the module, we find all of them listed as ports. And this means that we can directly connect our implementation to these ports in order to communicate between the inner part of the component and the external part of the component. So here we can design the full adder using gates. So we use logic gates to implement the functionalities of a full adder. Here I don't want to go through the theory because I assume that you already know the theory and how a full adder can be implemented, but I want just to show you a few slides that were already presented during previous classrooms and during other lectures. So this is a first cut implementation of a full adder. Actually, this is just the sum bit obtained starting from A, B, and C in. And then we also have here the implementation of the combinational circuit which provides an implementation of the carryout. And we can put the two together in order to find an implementation of both the carryout and the sum bit. And this is a possible implementation. Notice that we can start with this implementation, which makes use of the results of the logic synthesis performed in these two previous slides. So we can take this as a candidate implementation for the sum bit, and this as a candidate implementation for the carryout. But then if we put the two together, we can find a better implementation which reuses the result of the XOR between A and B computed as part of the combinational circuit which computes the sum bit in order to simplify the logic circuit which provides the carryout. Moreover, we can decide to use an AND-only implementation of the carryout plus the two XOR that we have here. So this is our reference design, and we are following this scheme for our implementation. But instead of using the logic gates which are directly provided by TKGate, I want to reuse the components that the gates actually, that we designed in the first video tutorial. So please refer to the first video tutorial to see how these components can be implemented. And in the meantime, I show you that you can even download the result of the first video tutorial from the website of Informatica Applicata, Applied Computer Science. So this is the URL, and this is the file that you can download. The reason why I'm pointing to this file is that this file, which was generated as a result of a design, can now be taken as a library in order to reuse the component that we developed last time. So let me show you how to do so. We can go here under File and select Open Library. And we can reopen the myxor.v file as a library. And in this case, it does not appear as a design in our page, but it appears as available library modules. So this means that if I want to use an XOR and I want to reuse the XOR that we designed last time, I can go here and under the Make menu, I can select module instance, and if I specify my XOR, here is the XOR that was designed last time, and if I go inside this XOR, I find the design of the component with our custom CMOS gates that can be opened, and in this way we will end up having a full-fledged design based only on PMOS and NMOS transistors without having to redesign the components that we designed last time. Okay, let me go back to this level in which we are trying to implement a full adder. So we need two XOR gates. So I make another one. And then we need also several NAND gates that were developed as a byproduct of the design of the XOR last time. So module instance, main end, and here it is. We need 3 of them. And here we are. So notice that this is our reference design, and so as you can see, we need 2 XOR to compute S and 3 NAND gates to compute the carryout. So those are the 2 XOR gates. And I have also to add module inputs and module outputs. Please make sure that you use exactly the same names that you used when defining the interface of the modules, or otherwise this connection won't be recognized. Make module output, the last one is the carryout, and here we are. So I connect the sum bit to the output of the second XOR and the carryout to the output of the third NAND gate. Then I start connecting the components together. So those are the XOR. Okay. Then I have again, let me show you the reference design. As you can see, I have also to connect A and B to the first level NAND gate, and then at the second level NAND gate I need to combine the carry in together with the XOR of A and B. Okay? So at the first level, just A and B. At the second level, I have the carry in and the XOR. Then at the third level, I combine the output of the 2 NAND gates into the last one. And here we are. So this is our implementation of a full adder. We can test it before going ahead. So if I go back to the top level, I can add the switches and LEDs in order to test the functioning of this first component, which will then be reused 4 times in order to put together a 4-bit full adder. So from the IO library, I take as many switches as I need, 3 in this case, and 2 LEDs to represent the results. I connect all the components together. Oh, sorry. Okay, here we are. Now we are ready to test it. Begin simulation. The fact that the simulation started without any error or warning means that we didn't make any formal error, but now we need to test the functionality. We need to make sure that the design that we implemented actually implements the functional specification of a full adder. So to this purpose, we need to make sure that for all possible input configurations, the outputs are correct. So let's see what happens. If all the input bits are 0, then both the sum bit and the carry out take value 0, and that's correct. So let's keep the carry in to 0 and see what happens if we change A and B. So with A taking value 1 and B taking value 0, the sum is 1 and the carry out is 0. In the other case, B equal 1, A equals 0, the result is the same, and if both A and B take value 1, then the sum is 0 and the carry out is 1, which is correct. Now let's see what happens if we raise the carry in bit. Having also a carry in case of A and B taking value 1, the sum of the three ones is 3, which is 1, 1 in binary. So both the carry out and the sum bit take value 1, which is correct. Now, if we have just one of the two input bits at 1 together with the carry in, then the result is 0 and the carry out is 1, and in the other case as well, while in case of having a carry in with both A and B taking value 0, then the sum is 1 and the carry out is 0. So our full adder works properly. So this means that we are ready to use it, to compose 4 of them in order to realize our 4-bit ripple carry adder. So let me get rid of oops, sorry, I need first to stop the simulator, and I can get rid of all the primary input and output, and then I will probably have to reuse them, but I won't use just switches and LEDs, but more convenient input and output components once I have developed the entire 4-bit full adder. So this will be the first full adder, which means the full adder in handling bits in position 0. Then I need to have another one in position 1, which is this one, another one in position 2, and another one in position 3 here. So those are the 4 components that I need, and this is the way in which they need to be concatenated, in such a way that the carry out of a full adder provides the carry in to the subsequent one. Okay, let me adjust them a little bit. Oops. Too bad. Okay. This one as well. Good. Here is our component. Now, instead of having these 4 components at the top level, I want to put all of them within another module called Ripple Carry Adder 4. So, to this purpose, I want to add a module make module instance, which is called my ripple carry adder 4. And this will have a carry in corresponding to this one, and a carry out corresponding to this last one. Then this module has also 8 other input bits and 4 output signals, which are the 4 bits of the sum. So I could add as many input ports as the input bits, or otherwise I can do something which is, let me say, much more readable and practical, which is defining a port which has a 4-bit parallelism. So I can add an input called B, the bit width of which is not 1 but 4. And I can do the same for A. So add input, I name it capital A, and I say that the bit width is 4 rather than 1. And I do the same for the output port S. Add output, I call it capital S, and I specify that the bit width is 4. Okay, this is our component. And within this component, I will report the design that I have here at the top level. So let me select all these components and copy them in order to paste them as an implementation for this component. Oh, I forgot something which is very important, as you probably remember, which is setting the interface of this module. So let me go inside this module and paste our previous design. So here we are. Now we need to connect all these nets here to the input and output ports of this component. And notice that the 4-bit ports A, B, and S are represented here as arrays of signals, having indices from 3 to 0 each. Okay, so now I can add a module input, and if I specify A, I obtain an A which is not this one, because I specified just bit width 1. What I need to do is to edit the properties and to specify that the bit width of this port is 4 instead. And I do the same for B, specifying directly the proper bit width in this way. While for C, the bit width is actually 1. For Cout, it is 1, while for S, it is 4 again. Okay, we have a problem now. The problem is connecting 4-bit ports to single-bit nets. Let me show you how to do so. Okay, let me start from the easiest part, which is connecting the single-bit input and output ports used to propagate the carry. And now we have to deal with the 4-bit ports. Okay, first of all, I extend this line in order to reach all the full adders by going over all of them. And now look what happens if I bring the end of this net to this 4-bit line. So what happens is that there is a connection between the 4-bit line and the single-bit line, and the same happens if I do it for all the A ports of the full adders. Also notice that near the connection point there is a small number. This small number represents the position of the bit of the 4-bit line which has been connected to the single-bit line. And in this case the number is always 0, meaning that all the input ports of the full adders have been connected to the bit in position 0, which is the least significant bit. So in order to make it work, I need to connect each full adder to a different line taken from this input port. And to this purpose, I can double-click on the connection point and under Details, change what is called the bit range. So I specify, instead of 0, 1 for this full adder, then 2 for this one, and 3 for this one. Okay, we repeat the operation for the other operand called B. First, we connect all the input nets, and then we specify the proper bit. Oops, I'm sorry, I'm not doing it very well. Oh, too bad. Okay, let me try with a different one. First, okay, good. Okay, and that's it. Now this is bit 1. This is bit 2. And this is bit 3. Okay, now I have to connect the 4 output bits to the 4-bit output port. Unfortunately, this cannot be done in the same way, because I cannot directly connect a 1-bit driving net to a 4-bit driven net. Or actually, apparently I can do so, but if I run a simulator, then simulation doesn't work. So instead of doing so, I need to do something different, which is this. So I need to take a specific component which is called wire merge. I'm sorry. And I have to edit its properties to specify that this wire merge has to provide a 4-bit output and to take 4 inputs. So let me go here and change the bit width of this net, and also go here and edit the ports by adding ports. So notice that I can assign a name to the wires, so I can provide a name here, or I can just add unnamed ones. Oops. me call it I add another one, and I can edit this one if I want, and I can call it bit 3. Okay. And there is the result. Now I can connect this output port to the 4-bit wire merge component, and then I need to carefully connect the 4 output bits to the input bits of the wire merge, respecting their positions. So this is a 0, which has to be connected to the least significant bit of the wire merge component. I do the same for all the output bits, and here is our result. Now, this is the implementation of the top-level module, which was called my ripple carry adder 4. So if I go back to the top level, I can get rid of this because now this has been encapsulated within this component. So let me double check. Here it is. So now I can use it. And to use it, I need a switch here to drive the carry in, and I need also a LED to show the value of the carry out. And then I need to provide 4-bit inputs and to show a 4-bit result. So to provide 4 bits at the same time from the input-output library, I take a dip switch instead of a switch. And this dip switch, if I edit the properties, has just one port, which is a 8-bit port. So instead of having a 8-bit port, I want to change the bit width and having just a 4-bit port. I do the same here, make input-output a dip switch. I change the bit width to 4, and this component provides directly a 4-bit input, which can be taken as an operand. As for the output, I try to do the same using either a LED bar. Let me show all of them. A LED bar, and in this case I want to change the input, the bit width of the input port to 4. But there are other ways of showing the result. So I can also select an hexadecimal 7-segment display, and in this case, if I change the bit width, the input bit width to 4, let's see what happens. That there is just 1 digit, because 4 bits correspond to just 1 hexadecimal digit, because both of them can take 16 different symbols or configurations. Then I can also decide to represent the result as a decimal number, and in this case, if I change the bit width to 4, then the number of digits is 2, because to represent numbers from 0 to 15, we need 2 decimal digits. What is nice is that we can use all these output elements together to see the result, because they are not mutually exclusive. Okay, now we are ready to simulate our circuit. Begin simulation. Oops, there is something that doesn't work properly here. So pin S on modular is not defined, and there are no gates driving net W6. So let's see what happens. Okay, so the problem is here. We have a module, a pin which is not defined, and no gates driving this net. In fact, if this port here is not recognized, then this net is not driven. So let's go inside this module and see what's wrong. Okay, you see where the error is. I forgot to rename this output port, which is called W4 instead of capital S. So I need to edit the properties and rename it S. Now I go back to the top level and restart the simulator, and now it works properly. Okay. With inputs 0 and 0, the result is 0. If I write 3 here, the result is 3. And notice that 3 plus 0 is indeed 3. And 3 is represented here in binary, which is 0011, in hexadecimal and in decimal, which is in both cases either 3 or all 3. If I change this to, for instance, 6 and apply it, then the result becomes 3 plus 6, which is 9. 9 is 1001 or 9 in hexadecimal. If I put here 9 and apply, then the result is 12. It is 12, which is 3 plus 9, and 12 is in binary 1100, while in hexadecimal is C, and in decimal number is 12, 1, 2. Okay, so it works properly. Now let's look what happens if instead of having 0 as a carry in, we switch it to 1. So the effect is adding 1 to the result. In fact, the carry in is like a 1 added in the least significant position. So this means that it corresponds to a third operand taking value 0, 0, 0, 1. So it is exactly as if we added a third number taking value 1. So we can use the carry in to add an extra 1 to our result. Okay, before completing the tutorial, I want to show you that now this component, which is a ripple carry adder corresponding to our original specification, can be used to build ripple carry adders of more than 4 bits. In particular, we can build a 8-bit ripple carry adder by using 2 4-bit ripple carry adders, thanks to the fact that the ripple carry adder has a carry in and a carry out port. So to this purpose, I can take this, or I can make another module called my RCA4 to show you that this is exactly the module that we have just developed. And I can take 2 of them, so edit, copy. Oops, I did something wrong. What's wrong here? Oops. Okay, let me undo it. Okay. So this is the one that I want to copy and to paste here. Okay. And now I can just connect the carry out of the first ripple carry adder to the carry in of the second one. And in this way, the concatenation of the two 4-bit ripple carry adders work as an 8-bit ripple carry adder. To show you that it works properly, I can do this way. I can take a 8-bit deep switch as operand A and another 8-bit deep switch as operand B. And notice that now they are 8-bit instead of 4-bit inputs. So I cannot use them directly, but I need to split them into two parts and to provide the least significant bits to this ripple carry adder and the most significant bits to this other one. So to this purpose, I need to edit the details, and instead of specifying from 3 to 0, I need to specify from 7 to 4 here. Then I do the same for operand B. Details 7 to 4, which is the second half of this word. And here I have to compose the two words into one word, and in this case I use just a decimal display, which is 8-bit, and I need a wire merge to merge the two 4-bit outputs into an 8-bit word. So I take a wire merge component and I specify here that the ports have a different bit width. So this has bit width 8, this has bit width 4, and this has bit width 4 as well. Okay, now this component here can be directly connected to this, while this has to be connected to the least significant bits, which are these ones, and this has to be connected to the most significant bits, which are these ones. Then we need a switch to drive the overall carry in, and a LED to see the status of the carry out. Let me start the simulation again, and let's play with it. So I can say that here we have, for instance, number 35. Having 8 bits, I can specify any number from 0 to 255. So here I can write 78 and apply, and the result is 78 plus 35, which is 173. It doesn't sound very good. There is something wrong somewhere, because 78 plus 35 is not 173. So what's wrong? Let's see what's wrong. So first of all, let me stop this and see which are the properties of these ones. So this is the switch value, and see what happens if we specify begin simulation. Okay, we specify 255. As you can see, this doesn't work. Do you know why? Because this is indeed hexadecimal. So this means that I can specify here A, and I can specify here A again, and this becomes 20. So while this is specified as a decimal number, the inputs are hexadecimal numbers. So this means that if I want to specify, for instance, 16, I have to specify here 1, 0. Oops, sorry, 1, 0. And if I want instead to specify 15, I need to use F. Or if I want to specify 255, I need to specify FF. Okay, and so on. Now, what we can do is to see, oops, sorry, what happens if we specify 1, 0 and 1, 0, and the result becomes 32, which is correct. If I specify instead, as I did before, FF and apply, see what happens. Instead of having 255 plus 10, which is 265, I have here apparently a wrong result, but the carryout LED is set to 1, meaning that there is an overflow, which means that the result is no longer an 8-bit number. In fact, 255 is the biggest number that we can represent with just 8-bit. If we want to add something to 255, we obtain a number which requires 9 bits to be represented. And this is out from the range of the numbers which can be represented in this display. So this LED here has to be taken as an error message or as a warning or as an overflow flag saying that the result is incorrect because the operands were too big to be processed by this 8-bit adder. Okay, that's it for today. This concludes our tutorial, and I look forward to meeting you at the next one. Bye-bye.